Hey everybody, welcome back to another round of physics and yeah, let's get going. As the title would suggest, it's time for us to talk about light. So, the question, we have Maxwell's equations and the question becomes what relationship has to exist between the electric field and the magnetic field for both to propagate in the absence of currents and charges? In other words, I would like to know what happens if there are no charges present and there are no source currents present. There's nothing to actually produce electric fields or magnetic fields as we have examined thus far in class. And so we'll go ahead and let us apply Faraday's law. We will go ahead and apply Maxwell's correction and to see what relationship must exist between the electric and the magnetic fields. Now I have set up for you here our starting point. So notice we have our axes, y, x, and z coming out of the board. Please take particular note of that because for the second half of this derivation, we'll take our vantage point from where it currently is and we'll rotate to be looking down the y-axis. So that's the first thing that I want to point out to you. The second thing is I have defined a loop around which we will calculate the path and also the flux of, in this case, the magnetic field. You can see that the magnetic field flux is this area here labeled A and has been grayed. And notice that the remaining portion of that rectangle, it has no magnetic field present. So I'm only considering the magnetic field in this region that's at the center of the screen. However, I'm going to give this region a very interesting property. I am going to say that this slab of electric and magnetic fields, I am going to say that it is propagating to the right at some speed, v. And I would like to know what is the relationship between E, B, and V that allows this slab, this region of electric and magnetic fields to continue propagating. You ready for it? The first thing that we're going to consider, I have it for you here, but the first thing that let's consider is let us consider the flux of the magnetic field. Now this should feel rather familiar. Rather than thinking about this slab of electric and magnetic fields moving in space, you could, for example, think of it as being stationary and I take a rectangular loop of wire and shove it in, right? We've done that problem in homework. Of course, I say rectangular loop. Right here, previously we had actual physical wire made out of copper. Here I'm asking you to conceptualize taking a rectangular loop made out of nothing and shoving it into the magnetic field. So we will dispel with the pleasantries. We know that the magnetic flux will be given by the H, X, and the magnitude of the magnetic field. We'll go ahead and say that n hat is pointing in the z direction parallel to the magnetic field. And so we know from our previous work that the change in the magnetic flux must be equal to the height of my rectangular loop, the magnitude of my magnetic field, and the velocity, I should say speed, the speed at which this region is moving. Well, let us now go ahead and start thinking about Faraday's law. Now, I'll go ahead and say that there is a difference in potential that is generated due to the changing flux of the magnetic field. And let's go ahead and get rid of that pesky negative sign for a second. We know that as this field moves from left to right, that there is an increase in flux in my rectangular loop. Well, because there's an increase in magnetic flux, there will be an induced current, put in air quotes because we don't have a conductor, but there'll be an induced current that will run in such a manner to oppose that change. So if I think about that, I need an induced magnetic field that points into the board. And therefore, my current must be moving clockwise around this rectangular loop, what I would previously have called the induced current. That direction ensures that there is a magnetic field induced going into the board. Okay? So I've taken care of that negative sign. Okay? The reality is I'm going to go ahead and, let's get rid of that. Okay? Now let's go ahead. I've substituted this in. We have H times B times V. Okay? And now I wish to actually determine this side. Well, we've already determined the direction that the induced current would have flowed had this loop been made out of a physical conductor. But you know that the direction that the current would have flowed must be from a high electric potential to a low electric potential side, or conversely, that the electric field must be pointing in that direction. Right? Goes along the line of electric field. So I will go ahead and integrate around the loop in the same direction. In other words, I will take this as being my direction of dl. Well, because the induced electric field is parallel to dl, I will have that the magnitude of my electric field times, so H is equal to H times B times V. And we say, oh, goody, goody. Yeah, the H's cancel out. We get something that says there is an induced electric field that is equal to the magnetic field strength times how quickly the slab is moving. Okay? Let's keep that on the back burner. Okay, put that off to the side. Let's keep that on the back burner, and let's go to the next thing. Okay? Now here, I am going to rotate. I already warned you, we're going to rotate, and now we're going to be looking down the y-axis. Okay? So let's think for a second. That means if we are looking down the y-axis, that means that now, rather than the magnetic field be coming out at us, it is the electric field that's going to be coming at us. And because we're rotating again, we'll see that rather than the electric field being pointed towards the top of the page, we'll see it's the magnetic field will be pointing towards the bottom of the page. Okay. Now practice that for a second. I mean, I have it drawn on the next page, but just imagine taking your vantage point, rotating up to the y-axis, looking down the y-axis. What do the electric field vectors and the magnetic field vectors, which way are they pointing? Okay, that's always a good exercise. Okay, here we go. So we are going to play the same song and dance. Okay, but here, rather than thinking about Faraday's law, I said we are going to be thinking about Maxwell's correction. dl equals mu naught E epsilon naught d phi E over dt. Okay. Now again, we can do the same song and dance. We see that the electric field is coming out of the board towards us. So I will go ahead, E is out of the board, and we will go ahead and take n hat. We have a choice. We will also take it out of the board. Okay. Now, I should mention here, we are free to choose the direction of n hat, and I'm choosing it to make my life easier. But once we choose that direction, we have to be careful because the direction of dl ends up becoming fixed. dl depends on which direction we've chosen for n hat. We saw that when we took Lenz's law into account here. Okay? So here, I'll again be careful. We know that the electric flux, well, is also given by the area times the electric field. Again, the electric field being constant for this particular situation. And we find that it is, again, x times h times the magnitude of the electric field. And so the time derivative, as we would expect, is the speed of that slab times h times e. Well, that seems kind of redundant. Okay. Now, the electric field is increasing, the flux, and because we don't have a negative sign, that means that the induced current should run in a manner to increase that electric flux. Okay, maybe not induced current. Okay? What I want to say is that the magnetic field, there should be a magnetic field that's generated. And if I were to try to assign a current to that induced magnetic field, the current should be running in a direction to encourage, entice, to cause, to increase the electric flux. Okay. So by that, I mean, okay, the induced magnetic field is going to, well, you could think of which direction would a current need to run in order to increase the electric flux? You'd say out of the board. So you could think of there's like a displacement current coming out of the board. And then if I think about the magnetic field due to that displacement current, I would get a magnetic field that is circulating counterclockwise around my loop. And so that's the direction of my DL. Okay, well, again, we go song and dance. This is the only part of the loop that experiences that magnetic field. And so we can think of writing this. BH is equal to mu naught epsilon naught VH magnitude of E. We say, oh, goody, goody. Yeah, you see it. The H's cancel. And so from this treatment, we get that the magnitude of B is given by mu naught epsilon naught V E. In other words, we have a relationship, one relationship, between B, V, and E. Well, from the previous case, we had a second relationship. Let me write those down for you. And now, as I suggested, let's take those two results and combine them. I'm going to take the relationship between E, B, and V that I found using Faraday's law, and I'm going to substitute it into the relationship that I found for B, E, and V that I got from Maxwell's correction. And if I combine those two, something strange happens. And you see it, I hope. There's a goody-goody moment. My B and wait, I got rid of my E's, and I have a goody-goody moment. My B's cancel. And what do I find? I find that I have 1 over mu naught epsilon naught square rooted is equal to the speed. My slab, my very contrived slab of electric and magnetic fields has a restriction. That slab, that region of space that has electric and magnetic fields, must travel at this speed. Go ahead. Put it in your calculator. You know that mu naught is 4 pi times 10 to the negative 7th Tesla meters per amp. You know that epsilon naught is 8.85 times 10 to the negative 12th. Let's see here. It would be coulombs squared per Newton meter squared. Go ahead. Plug those values in. What do you get? Yeah. Hopefully you see it. You get that mu naught times epsilon naught, 1 over this. You square root it. You'll get a strange value. I'll round. I don't have a calculator in front of me. But you'll find out that if you plug those two values in, you get 3 times 10 to the 8th, and units will be meters per second. Notice that if you have, regardless of the electric field strength, regardless of the magnetic field strength, the only way for this slab to propagate through empty space, no charges, no currents, this slab propagates through empty space at that speed and only that speed, otherwise known as the speed of light. Okay? And that's why we call those Maxwell's equations. Without the Maxwell correction, we would have no complete model of the electromagnetic fields, and therefore we would be without a good model for what light really is. Now bear in mind, Maxwell's doing this in the mid-1800s. The nature of light is not well known. In fact, one of the questions of the day is, how does light from the sun propagate to the earth? So Maxwell puts this all together, and he has a theoretical framework which suggests that light travels at a particular speed in vacuum. Okay. Now, the connection, this is a theoretical framework. Where we really come down with it is that the speed of light was already known at that time. In fact, Galileo had an attempt himself. His attempt was fairly straightforward. How we measured the speed of light even afterwards was the same idea. It's just the timing, the technology got better. Galileo proposed simply having two people on distant mountaintops. And the idea was straightforward. One person had a lamp. Actually, they both have lamps, one of which is covered. Okay? And what happens? Well, I should say both of which are covered. Now, what happens? When Galileo gives the indication, the first person uncovers their lamp. Okay? At which point in time, the second person is instructed that once they see the first lamp uncovered, they are to uncover their lamp. And then Galileo would observe the uncovering of the second lamp and stop his watch. I say stop his watch, but starts taking time, counts the ticks of a pendulum clock, and determines how long it takes for the light from the second lamp to come back. Okay. Now, of course, they need to measure the distance. And so the idea is, if I can measure how long between the uncovering of the first lamp and the reception of light from the second lamp, then I can simply find the speed of light. The problem with Galileo's experiment is that it happened essentially instantaneously. Galileo, I believe, came down to the conclusion that if light has a finite speed, it is very high. That's basically the best he could do. In fact, it's very hard to do this kind of measurement unless you have very, very fast timing devices, or if your distances are really, really large. It turns out that Oil Roemer, an astronomer, actually had data to find the speed of light. He was observing how quickly Io would orbit Jupiter. His idea was actually tied to celestial navigation, using the stars to figure out one's position on the Earth. It was thought at the time that perhaps the orbit of Io around Jupiter could serve as a universal clock visible to people at night, and maybe that could serve as a mechanism for synchronizing watches. The issue is that Oil Roemer noticed that the period of orbit of Io around Jupiter was inconsistent. And by this I mean that when he noticed in his notes that when Earth is approaching Jupiter, his predictions of where Io should be were off. They were too early. But when Earth was receding from Jupiter, he noticed his predictions of where Io should be in space didn't match his observations. His observations were finding Io was too late in comparison to his predictions. And it turns out the reason for that was that his predictions didn't take into account that light takes a certain amount of time to arrive to him. In fact, I believe a French astronomer, Cassini, pointed out that the delay, the mismatch between his observations and predictions, could be accounted for by if light had a finite propagation speed. It's not until the 1800s that two gentlemen by the name of Fizeau and Foucault are actually able to measure the speed of light within, say, about 3% of its accepted value today. Now, how they did it was similar to what Galileo did, the only difference being that, for example, Foucault used a spinning mirror, a six-sided mirror, and what he would do is he would shine light, it would bounce off one face, go some different distance, come back, and bounce off and go into his detector. And in the time that it took the light to travel, I believe he did something like 12 kilometers. And of course, he sets up a mirror. In the time that it takes light to travel the 12 kilometers down and back, the mirror spins exactly 1/6 of the way around, so that the original reflecting face is the rebound face, the second face that the reflection occurs off of. And this gave him a way of accurately measuring the timing intervals. In other words, he knew how quickly the mirror was spinning, the angular speed of the mirror. So he would know that the time that it takes, if he knows the angular speed, he knows how long it would take the mirror to rotate 60 degrees. And therefore, he could say what the time interval was. Now, this is an example. I think he used like a 100-sided mirror, but the same idea holds. So at the time, experimentally, the speed of light was known. And so that's where the connection comes in, is that Maxwell, through his theoretical framework, finds a value that resembles very closely the speed of light that has been determined experimentally. And so the connection is finally made that perhaps light, that perhaps light is actually an electromagnetic wave. I should point out here that this idea that the speed of light is constant from the theoretical standpoint, it still took about 40 years for that idea to firmly ferment in scientists' mind. In fact, up until 1901, Michelson Morley did not necessarily believe the speed of light was constant. I mentioned this idea about searching for a medium through which light travels. Maxwell was able to show, from a theoretical standpoint, that no medium was necessary. Still, scientists were troubled by this, and they kept searching for the mysterious medium through which light propagated. Perhaps it actually exists, it's just that we haven't been creative enough to measure it yet. Michelson Morley in, I believe, 1901, put to bed that a medium was needed. They designed an experiment. I won't go into details here. Please look it up. It's not particularly difficult. They designed an experiment to measure the speed of the medium through which light traveled. And it's probably the most famous null experiment ever. They were never able to actually find the influence of the medium on the speed of light. Another scientist finally put the nail in the coffin. He said, rather than us searching for a medium, which is not necessary from a theoretical standpoint, why don't we just assume that a medium doesn't exist? And furthermore, the theoretical standpoint tells us that the speed of light is constant. It's a property of empty space. And if we take that to be true, then we have some very interesting consequences. For example, that time is different for people moving at different speeds. That statement is the fundamental bedrock of a branch of physics called special relativity. And of course, the famous scientist that proposed that the speed of light is truly constant and then went through and showed some of the physical ramifications of that is none other than Einstein. Hey, if that's not a plug from taking modern physics, I don't know what is. So hey, I thank you for your attention. Keep up the good work. I'll see you next time.